Welcome everyone. This is an introduction to non-linear systems. The introduction will consist of two parts. This video is part 1, while a coming video will be part 2. In part 1 we are going to define and introduce the dynamical nonlinear models that we are going to see in through this course, and we'll see that the nonlinearity of the models has to satisfy a basic property which is called the Lipschitz property. That property could be satisfied either locally or globally. We are going to define what does that mean. However, we will see in part 2 that the Lipschitz property actually would be the key properties that we have to ensure in order for the dynamical differential equation that describes the nonlinear system to have a solution, and that solution should be, of course, unique. Once we do that, we will move to another concept that we are going to deal with frequently through the course, and that's the concept of equilibrium points. We define the meaning of equilibrium points and how to calculate them, and we'll take some examples to illustrate how we can, for a certain physical system, develop a standard nonlinear model, study its Lipschitz property, and find its equilibrium points. So as a start, let us see how we can mathematically represent nonlinear models as a set of first order differential equations. Typically, we will have the nonlinear models in the form of a set of first order nonlinear differential equation. So for example, the first equation is x1 dot equals f1 of t x1 up to xn and u1 up to um. So we define here x1 as the state variable, and x1 is a real valid signal, so we say that it belongs to the real numbers, and we can form a vector x which is composed of all the state variables from x1 up to xn. Consequently, we say that x belongs to the real space but of dimension n. u1 up to um would be the external input or feedback control signal, and again we can put that in a vector u which is composed of m components, u1 up to um. So we say that u belongs to Rm, and of course we have the time t which is belonging to the real numbers in general. So if we have this set of nonlinear differential equations x1 dot up to xn dot, we can also write the set of equations in a compact form. X dot equals f of t x and u, and in that case f is called a vector field, and it belongs to again a space of dimension n. So f here is a vector which is composed of f1 of t x y u, f2 of t x and u, and so on up to fn of t x and u. So that would be the vector. So this is the general, very general form that could represent a nonlinear model. If we have x dot equals f of t and x only, we say that this is unforced system. If we have x dot equals f of x, we call that system autonomous system. And autonomous systems actually are equivalent to time invariant systems, while x dot of f t and x, this is called non-autonomous system. And this is equivalent to the time varying systems in the system analysis or system signal analysis representation. We could also have another function h that relates the measured signals to the state variables and the input. And in that case, we would have an extra equation, which we call it y, as a function of t, x, and u. This function is called the output equation, and y could be a signal that a vector signal that belongs to a space, a real space of dimension say q. The difference between y and x would be that y are measured signals, while x are the state variable signals of the system in general. Example, let us consider the simple pendulum equation of motion. So we have here assume that we have a rod with length L, and the mass of that rod is concentrated at the end with a value m, and there is a pivot here around which the pendulum can rotate. The angle of rotation measured from the vertical position is theta. So if we would like to write the equations of motion, we can just apply Newton's law, and that would lead to m L squared theta double dot equals to, if we assume an external torque T applied, then that would be the driving force, and opposing to that would be some friction due to the rotation around the pivot, and that could be represented by friction constant, say k times L squared theta dot, which theta dot of course is the angular velocity, and another opposing force due to the gravitational force, and that would be mgl sine theta. Of course, this system is nonlinear, and the source of nonlinearity is the sine theta term which appears in the modeling equation. Now, our purpose is to put this nonlinear equation in the standard form, which is a set of first order differential equations. So in order to do that, let me first write the equation for theta double dot, and in that case it would be, say, minus k over m. I'll divide by m L squared minus k over m theta dot minus g over L sine theta plus 1 over m L squared times the torque T. Let's call k over m some constant b. I will call this term c, and I will call this term d. So I can write theta double dot equal some constant b times theta dot minus d sine theta plus c times t. So this is the modeling equation. Now, in order to convert this to a set of first order differential equations, one method to do this is to take say x1 equal to theta, and x1 dot would be x2, and in that case it would be theta dot. So if we calculate x2 dot, it would be theta double dot, and this is from the modeling equation, would be minus b theta dot minus d sine theta plus ct, and we can substitute for theta dot by x2, so that would be minus b x2 minus d sine, and theta is nothing but x1, so it will be sine x1 plus ct, and this is the equation for x2 dot. Now we can put that in the vector form, so we would have x1 dot and x2 dot, and that would be the state, the derivative of the state vector, and that should be equal to the nonlinear functions. In that case, I will have two nonlinear functions, f1 and f2. So f1 is the equation for x1 dot, and that's nothing but x2, and f2 would be minus b x2 minus d sine x1 plus ct, and that is the vector that represents the nonlinearity f1 and f2. So this is the standard form x dot equals f of x and u, and of course in this example u is just the external torque applied to the system. So let us again consider the general system, which is given by a set of first order differential equations. X dot equals f of tx and u, and we assume that u is either a feedback signal from the states or some function of time, where that would allow some external inputs, which are functions of time, to be included in the equation. But if we have that, we can write the equation as x dot equals f of t and x, and we call that system the unforced system. Now in this course, most of the time we will be interested in studying this system. So we'll study the stability of the system, the equilibrium points of the systems, and so on. So in order for that study to be carried out, we have to assume that this equation, the differential equation, has a solution, and that solution is unique. It turns out that the existence and the uniqueness of the solution will depend on conditions that we have to impose on f. So the first condition is that f has to be piecewise continuous in t and locally Lipschitz in x. So in order to understand that local Lipschitz condition on the function, I'm going to give a definition and then some examples to illustrate it. So if we assume a nonlinear function f of t and x, which is defined over some time interval that is a subset of the real number, that function is locally Lipschitz if we can define a ball of radius r around a certain point. We call that point x node, so that if we take any 2 points within the ball and we calculate the norm of the function at the the norm of the difference of the function at the 2 points, that has to be less than or equal to some given constant, positive constant L, multiplied by the norm of the distance between the 2 points x and y. Now the norm could be defined in different ways, and one way is the Euclidean norm, where we take the square root of the sum of the squares of the elements of the vector. So let us start by drawing a figure to illustrate this condition. Of course, to make things easier, I'm going to assume that f is a function of a scalar variable x, so that we can draw it. So let us have here the x-axis, and here we have f of x, and I'm going to take a function like this. This would be the plot of f of x. Now assume that we select a certain point, any point like here, this is x node, and we take an interval around that point. So this is the distance that we called in the definition small r. So now we can pick up any 2 points. So I call the first point x, and the second point I call it y. So if we apply the definition, it says that the value of the function at x minus the value of the function at y divided by the difference between x and y has to be less than L. So actually f of x minus f of y over x minus y, this is nothing but the slope of the line that would join the 2 points. So the slope of this line is actually function of x minus the function of y divided by x minus y. So what it says here is that if we pick any 2 points and draw a line between the 2 points, then the slope of the resulting line has to be less than some constant L. If that happens, then we say that this function is locally Lipschitz at x node. Of course, in this specific example, we can calculate the derivative of the function f of x and take the maximum of the derivative between the 2 points, and the value that we get could be taken as the Lipschitz conditions, the Lipschitz constant L for this specific case. And what we have here is, of course, a locally Lipschitz function as I represented. So let us take some examples to illustrate how to study whether a certain function is locally Lipschitz or not. The first function I'm going to take is, say, a straight line minus 4x. So if we plot that, it would be of course a line with a negative slope like this. This is x and this is f of x, and the slope here is minus 4. So if we take any arbitrary point, I call that x node, with some interval around that point, and we take any 2 points within the interval, we'll plot a line between the 2 points, we'll always find that the slope will be minus 4, which means that we can take L equals to 4. Of course, L is the absolute value of the difference between the value of the function at the 2 points divided by the interval between the 2 points. So this is the case here, and this actually can be done at any point on the x-axis. That's why we call this function not only locally Lipschitz but globally Lipschitz, because the condition is satisfied at all the points x from minus infinity up to plus infinity. So this is an example of a function which is Lipschitz. Now consider another example, and in that example I will assume that the function is discontinuous at a specific point. So this is x and this is f of x. Assume the function is represented like this, where here at some value x node the function is discontinuous. So accordingly, if we take an interval around the function, around the value of x node, this is the interval that I'm going to take. and we take two arbitrary points like this, we'll find that the slope of this point will be changing as the 2 points move closer to the point x node. And as you get closer to the x node, the slope of the resulting line would have a slope approaching infinity, which means that in this interval around x node, we cannot really find an upper bound on the slope of the lines that we draw. That's why we say that at x node, this function is not locally Lipschitz. And the conclusion, a general conclusion that we can draw here is that a function f of x, which is discontinuous at x node, cannot be locally Lipschitz at x node. So at x node and around x node, any interval that would include x node can't be actually, you can't actually find Lipschitz constant for the function. So discontinuity is a reason that would make us exclude the point x node. However, if we take another point here, say x1, that point x1, we can find an interval around x1 where we can find the constant L that would be an upper bound on the lines that would be drawn between any 2 points on the function. So we say that the function is locally Lipschitz at or around x1, and so on. Another example, we'll take f of x equals x to the power 1 over 3. Let's plot the function. The function would look like this. It would have, this is x and this is f of x. So at 0 the slope is infinite actually. Let's see what will happen if we take f dash of x. That would be 1/3 x to the power minus over 3. So if we calculate that at x equal to 0, that would give us infinite. So if we take an interval that includes the origin, that includes x equal to 0, and try to find an upper bound on the slope of the line that will join 2 points within the interval, this L constant that we are always looking for, we'll see that as we approach the origin, the slope of the line that we would draw to join 2 points in the interval will keep increasing until it reaches almost infinity at the origin. So we cannot really find the constant L for this interval. So this is another reason that we would have in order to judge that a certain function is not locally Lipschitz. So we can draw some notes here regarding the conditions for a function to be locally Lipschitz. The first note is that if we have a function f of x which is discontinuous at a point x node, then it is not locally Lipschitz at x node. This is the first note here. The second, if the derivative of the function f dash of x goes to infinity at x equals x node, then again f of x is not Lipschitz at x node. We can also see that if f of x and f dash of x are continuous, at a point x node, then we conclude that f of x is locally Lipschitz. However, this is actually only a sufficient condition, not necessary, but sufficient condition, and I will give example to illustrate this point. Now, suppose that we have this function. This is x and this is f of x. As we can see here, the function is continuous. However, the derivative, if we plot f dash of x, so we'll notice that in this first part the slope is 0, and then the slope increases to some positive value, as you can see here. So that means that at this point x node, the slope is not continuous. So the condition that f dash is continuous is not satisfied. Still, this function is Lipschitz, because if we take any 2 points around x node, say this point, this line, we'll find that the slope of this line will be always less than the slope of the right line here or in the function f of x. So we can have an upper bound on the slope of the line determined by the slope of the original function straight line here. So what I'm saying is that the condition that if f of x and f dash of x are continuous, that would lead to locally Lipschitz condition. That's true. But even if f dash is not continuous, still in some cases we can show that the function is locally Lipschitz at x node. A final note is that if we have in general t in the interval J, which is a subset of R, and X in a domain D, which is subset of Rn, the function f of t and x and its partial derivatives which are partial fi partial xj are continuous, then f of t and x is locally Lipschitz, and x on D. As I said, this is a sufficient condition. However, if that's satisfied and f of t and x and its partial derivatives are continuous, for all x that belong to Rn, then f of t and x is globally Lipschitz in x if and only if the partial derivatives of f with respect to x are globally bounded. So this actually gives a general overview about how we can understand the Lipschitz conditions that will appear frequently in our statements of the analysis in nonlinear systems, and in the next piece of the lecture we will see how that affects the uniqueness and the existence of the solution.